afternoon, fancy meat computers. Wow, that's a new low in terms of viewership. There's a midterm at the same time, so did somebody book a midterm over my class or something? Well, 6 people. Ah, it's going up. Next week. Mark's here, at least. Anybody else besides Mark here? Ah, Daniel is there. Not as bad as SD3, lol. Yeah. What, the attendance? I take it nobody at all came to SD3. Has anyone logged in? Well, at any rate, I don't think there are any announcements for this class. Let me checkaruno. Checkarolio. Nope, no announcements. Because I still haven't made the announcement yet about canceling the midterm. 3SD4 had 4 people in the last lecture. Oof. Windows 11 is still a mess. Well, of course it is. Duh. It's Windows. It's like expecting a Windows operating system to work. You're like, you just need to lower your expectations, man. It's really interesting. The whole upgrade your operating system thing. I still think that's a huge racket to try to get people into new hardware. Like, I don't, like, maybe once or twice has a new version of an operating system required less memory. So generally speaking, when you upgrade your operating system, you're taking a hit on available system resources, which is why generally speaking I don't upgrade my operating systems. If they're Windows, at least. Linux, you get away with it, of course, because Linux is perfect. But you know, yeah. When I get my computer parts, I'm just building it with Arch. Yeah. Of course you use Arch. Of course you use Arch. That's okay. I know that I'm just a silly little Ubuntu normie. I know that. I will give them around 2 years to fix the bugs before I upgrade. Good plan. Good plan. Unix-based OS for the win, indeed. You really can't beat it. So, I think that we should continue on with our lectures, eh? Continue on with the lecture stuff. See if we can't get through this topic this week. Tremble in fear of your Arch powers. Yeah, well, I know who to come to. I know who to come to if I need any drivers fixed, eh? Alright, who to go to. So, let's talk about the safety of type systems. We were talking about this slightly before the break. It bears repeating. So, we just went to all of this trouble to iron out a type system. And one might ask the question, what is the purpose of the type system? Right? It's like we go to a lot of effort to set up this interesting thing we call the type system. Why? Why is this necessary? I understand from one of the TAs that that's kind of what some people think about this course in general, is like, why is this necessary? But, you know, students have been asking that about things people have been trying to teach them for as long as there have been students and teachers. So, you know. So, in general, the thing that we're trying to do with the type system is guarantee that anything that types will also execute. That way we can have a separate means of verifying the calculation before the calculation is executed, right? The whole point of this is to be able to build a type checker into a compiler so that the type checker tells you how correct your program is before it gets executed, before it gets particularly distributed to anybody. So, one way of going about this is examining the idea of type safety. So generally speaking, when you hear the word soundness in this class, it generally means the same thing as type safety. It's not the same as the definition for the soundness of, for example, propositional or predicate logic. That's a slightly different definition. In this class, safety and soundness are considered to be the same thing. The safety property is essentially if a term is well typed, it won't get stuck under multi-step evaluation. So if you evaluate it all the way down to a eventual normal form, that normal form will be a value. Because remember, under UAE, and we are still dealing with UAE here, we're not yet into lambda calculus territory. Under UAE, our definition of stuckness is a normal form that's not a value. A normal form to which no evaluation, relation, inference rule applies. So in general, we demonstrate safety using progress and preservation. So the progress theorem states that a well-typed term is not currently stuck. That is, it is either a value or an evaluation rule can be applied to it, assuming that it is well-typed. Cool. And our second theorem is preservation. That is to say, if we take one step of evaluation, if we take one step of evaluation from a well-typed term, we end up with a well-typed term as well, right? So you can see how, taken together, if we take both of these two theorems in combination, we have an inductive argument for the safety of our type system, right? If any well-typed term cannot be stuck, and any step of evaluation does not remove the property of a term being well-typed, then you can say, no matter what term it is, if it's well-typed, it can't get stuck. It can never get to a position where it can get stuck. Good. So, in order to prove this, it's going to be useful to have an idea of what's called a canonical form. Canonical forms are not, like, at the moment they're synonymous with values, but we're going to see, like, as we get into lambda calculus, that we're going to see that canonical forms are not necessarily just values, but yeah, so anyway. In order to prove the theorems on the previous slide, we will need to more tightly associate values with types. The canonical forms of a type are the values in our language which have that type. So, a canonical form is a value. It's basically a way of mapping back from the domain. It's a way of mapping back from the set of types to the set of terms. It's like, you know, I have bool, canonical forms are either true or false. I have nat, my canonical forms are either 0 or the successor of any numeric value. So yeah, does that make sense? Canonical forms? Like, you should have an idea, like, you should in your brain have already associated the various types with their canonical forms, because that's kind of like, it's kind of like in a person's brain as opposed to mathematics or a computer. It's like the canonical form is in some sense synonymous with the type itself, right? It's like, what is a Boolean? A Boolean is true or false. Like, it's like, okay, technically no. Technically speaking, Boolean is a type. True and false are elements in a set that is designated by that type. So, you know, it's like when you get into math land, you have to sort of pull these things apart to the breaking point. But, you know, human beings, generally speaking, think less boxy. Like, it's the way we think is more like concepts inform other concepts. So, you know, you should have a good intuitive sense of what a canonical form is. So, to prove the above, to prove that true and false are the only values of type bool, it's reasonably straightforward. We first address the two clauses individually, starting with the first. So according to UAE grammar, values have four forms: true, false, zero, and successor of a numeric value. For true and false, we can derive a Boolean type from clauses 1 and 2 of the inversion lemma. So if you look back at the inversion lemma, there we go. If true has a type, that type is bool. If false has a type, that type is bool, right? Similarly, if we look at the types that are derivable from 0 and successor NV, also via the inversion lemma, 0, if 0 has a type, that type is nat. So, and successor we need to work a little bit harder for. But, yeah. So for 0, we derive nat rather than bool for clause 4 of the inversion lemma. So 0 cannot be a canonical form of the Boolean data type. And for successor NV, we note from clause 5 of the inversion lemma that the term must have type nat and not type bool. So one might say, when the successor is well typed, that type is natural, right? Oh, full screen. Yeah, sorry. So when successor is well typed, that type has to be natural. It's not possible to have a well typed successor function that is typed Boolean. So fortunately, in our hypothesis for canonical forms, we can assume that we're dealing with a well-typed term, right? We can therefore conclude that only Boolean values are true and false. The only Boolean values are true and false. So, therefore, true and false are the canonical forms of the Booleans, because, you know, it's like proof. What do they call that? Process of elimination. The argument for the second clause is precisely symmetrical. You just say, oh, these both result in naturals and not Booleans, so bing, bang, boom. Everything works. So, sometimes I feel like this is like school life, you know? Demonstrate progress or draw 25. Ha! So, in order to prove the type safety of the UAE type system, let's address both the theorem of progress and the theorem of preservation separately. Let's prove these bad boys. So, we may now attempt to prove the progress of typed arithmetic expressions. If we state the theorem somewhat more rigorously than the previous way, we say, suppose T is a well-typed term of TAE. That is, T has some type for some type capital T. We may conclude that either t is a value, or else there is some t prime such that t evaluates to t prime. Alright, so we need to prove, essentially, that no matter what term you start off with, if it's well-typed, you can evaluate it one step using the operational semantics. So this is going to pull back in the operational semantics from our, our previous discussions of UAE. So we start off this proof by saying that all well-typed terms are well-typed because a typing rule applies to them. We can then proceed via a case analysis of our typing rules. So, you can say, we know that T has some type, right? Because this relation exists, it has to exist from one of the typing rules, right? So we can do a case analysis over them. I'm going to ask if I completely lost everybody. Have I completely lost you yet? Yes, no, or not completely. So, with respect, not complete, good. So with respect to those typing rules that apply to our values, right? Those would be t true, t false, and t zero. All three of these apply to t only if t is a value. So if t is a value, then the theorem is satisfied. Because, of course, we say we are concluding that either t is a value or there is some t prime such that blah, blah, blah. So if t is a value, then the theorem has been satisfied for that particular case anyway. Wow. Windows is becoming, like, increasingly authoritarian with these updates, eh? Jeez. So. Yeah. So this is fine. So these three cases we can sort of knock out without really having to think too hard about it. The rest, however, are going to require induction over typing derivations. So, first case, let's consider the typing rule t-if. If this guy is t-if, then we can draw certain conclusions about what t must be. In order for t-if to be applicable, then t has to be an if-then-else. Right? It has to be of the form if t1, then t2, else t3. And, additionally, we get the premises of t-if for free. So we can say with confidence, t1 is bool, t2 is t, and t3 is t. We have assumed that the typing relation already holds, so we get all of this information for free. This is a very important and useful technique in these proofs. This is how you get your premises for each of these cases. So, by the induction hypothesis, t1 is either a value, or there is some t1 prime such that t1 evaluates to t1 prime. So, if t1 is a value, it must be true or false. Because of the canonical form's lemma, right? So we just demonstrated that if the type is bool and it's a value, then it has to be true or false. In these cases, either e if true or e if false apply to t respectively. Remember, these are our evaluation rules for picking out t2 and t3, picking out that selection. If t1 evaluates to t1 prime, then e-if is applicable. So, in all cases, t is either a value or t evaluates to t prime. So in this case, basically what we've done is we've demonstrated, based on the fact that t1 has been typed bool, it's inductively on the idea that this guy is well typed and that progress holds, right, for the subterm. So if progress holds for the subterm, then we're good, right? Yeah, so it's not so much in this case that t is a value. T does evaluate, right? But if t evaluates, then it's also true that t is a value or it evaluates, right? Because that's how logic works. Good. Now let's do the successor. Just from the form of the typing rule of the successor, we can immediately state that t must be the successor of t1, and that t1's type must be natural. By the induction hypothesis, t1 is either a value, or there is some t prime such that t1 evaluates t prime. If t1 is a value, it must be a numeric value via the canonical form's lemma. T is therefore a value as well, right? If this guy is a value, and it's a numeric value, then the successor of a numeric value is also a numeric value. Therefore, the theorem holds in that case, right? Because it's a value. Otherwise, if t1 is evaluatable to t1 prime, then the congruence rule, e successor, is applicable. We can step inside of the successor function and evaluate it on the inside. So, if that's true, then there is some that means that there is some t prime such that t evaluates to t prime. So in this case, we've got one case where t is a value and one case where t is evaluatable. So the theorem still holds in the case of the successor. Now let's consider predecessor. You can see that these arguments are, reasonably... They all pretty much progress according to the same structure, right? You'll notice I'm reusing sentences between these slides. So, and, that's often the case with these types of proofs. You can often reuse parts of, previous parts of the proof to prove other parts of the proof, or at least as reasoning for other parts of the proof, when you're doing this sort of case analysis. So, t pred t1. t1 is typed natural. We can conclude this from the fact that the t is typed, or the typing rule that applies to t is t pred. By the induction hypothesis, t1 is either a value, or there is some t1 prime such that t1 evaluates to t1 prime, right? We're assuming it for the subterm. If t1 is a value, it must be a numerical value via the canonical form's lemma, right? We know it's a nat, so it's either 0 or some number of successors applied to 0. If t1 is 0, then e pred 0 applies. If it is if t1 is successor t2, then e pred successor applies. So we've got a rule for both of those cases. In either case, an evaluation rule applies to t. If t evaluates to t1 prime, the congruency rule e pred applies. Therefore, in all cases, t is either a value or t evaluates to t1 or to t prime. So you may notice that for each of these guys, we have lined up an evaluation rule for each case here, right? This isn't an accident. It is worth adding evaluation rules to your operational semantics in order to make your type system safe. right? So type safety is an extremely important design consideration, and if you don't have it yet, assume you're designing some language, right? If you don't have type safety, but you could achieve it by addressing one of these cases that's not addressed currently by an evaluation rule, like consider you didn't have a congruence rule with predecessor or something like that, right? It's worth going back into your operational semantics and adding the things you need to make this work, right? Like, it's very easy to sort of think of it's very easy to think of the operational semantics as like written on these stone tablets that I ascended the mountain, I spoke to God, and he said, "Here, take these tablets, show them code," and but in our case, it wasn't a code of laws; it was a code of code. But these languages you shouldn't conceptualize them the same way as the Ten Commandments, right? You should conceptualize these laws, you should conceptualize the manner in which your language is designed as being sufficiently malleable that if you notice a problem while you're doing one of these proofs, like you can't prove type safety because you're missing something, that means you should add it. That's the purpose of the proof, right? It's to verify that your language has been developed in such a manner that it's not fundamentally broken, Because working with broken languages isn't fun. Ask any Python user. Ah! And you thought I wouldn't bash Python this lecture. How dare you, sir? Alright. Proof of progress 5. Finally, we've only got one typing rule left. It's t is 0. From t is 0, we can conclude that t is 0 t1 and that t1 is of type natural. Bash. Yeah. Bash is kind of a broken language. Yeah. Oh, yeah. Bash Python. Ha! Yeah. Oh. I was trying to think of a pun with the Z shell, but I couldn't. ZSH, I couldn't think of one. Maybe someone in the chat can think of a good pun. Anyway, so, induction hypothesis. We know that T1 is evaluatable. So we know that it is... we know that if it's evaluatable... we know that if it's not a value, it's evaluatable. So let's break it by case. If it's a value, then it's either 0 or the successor of some other value. If it's 0, then is 0, 0 applies. Otherwise, is 0 successor applies. In either case, an evaluation rule is applied. It can be applied. Otherwise, we know that T1 evaluates to T1 prime. And of course, the congruency rule is E is 0 applies if that's the case. Therefore, in all cases, T is either a value or T evaluates to T prime. We may therefore conclude that for all possible well-typed terms, that term is either a value or it can be evaluated using an evaluation rule. Quote, erat demonstratum. There you go. Any questions about that? Any questions? Good. Someone's got a question, though. Hit me. Hit me with that question. I can see 8 people are still paying attention. It's like, are you still paying attention? Yes, no. I know, it's Friday. It's a Friday afternoon. Nobody wants to be here. Anyway. If you don't ask a question, I can't answer it. Okay. So, proof of preservation. I have to say that, like, having 8 people out of a class of 120 actually paying attention to the lecture is, like, you know, or 9 people out of a class of 120. That's not a huge number, you know? I guess people have just decided that my my class doesn't mean any, or my class isn't useful, or it's not as, you know, it's not as useful to come to this class as some other class, but okay. If a term is well-typed, it can't get stuck. That is, we reach a normal form without having reached a value. No, other way around. If a term is well-typed, it can't get stuck. That is, from this term, we reach another term, right? And that, like, that's the idea with just the preservation, or just the progress theory. So we break it into 2 properties, right? The first property is that if you're well-typed, you're not currently stuck, right? And then the next one is, if you're well-typed and you evaluate, the next one is also well-typed. The implication being, then that one is not stuck, then you can go, then that one's not stuck, then you can go, then that one's not stuck. So you can follow, like, it'll be well-typed until it hits a value, and it will not get stuck. What is the purpose of proving the progress theorem again? Well, how do we know that our type system is sound unless we prove both progress and preservation? We are skeptical scientists. We do not take anything for granted. You should not believe me when I say this type system works. You should require me to demonstrate that, right? So this is how we demonstrate it. Yeah. So, let's talk about preservation. So the proof of preservation is a little bit more complicated than the proof of progress. You can tell by the fact that it's a bit longer. So the preservation theorem states somewhat more rigorously, if you were to write it out in sequent calculus, for example, T has some type T, and T evaluates to some T prime, implies that T prime has some type T. Isn't a value a kind of normal form? Yes. A value, like, the set of values is a subset of the set of normal forms, right? People watch recordings so they can rewind the video so they can make notes and learn at their own pace. Yeah, well, I mean, I have a certain amount of sympathy with that, but, you know, it's kind of depressing just to be talking to, like, under a dozen students, you know? Especially when 10 times that number of people are in the course. So, yeah. That's okay. We can have a good time as long as there are at least 3 students in the class. Is successor true a normal form? Yes. It is a stuck term. Stuck terms are also normal forms. So that's the idea, is that we can't, like, successor of true cannot be well typed. We don't have a typing rule for it, right? So that means that, well, we're not going to make any assumptions about whether or not it can execute. We're not, like, what we're not saying, we are not saying that if it's not well typed, it can't execute, because that's not true, right? That would be you got the barrier between the typed terms and the untyped terms to land exactly along the wrong terms. which is very, very, very difficult to do. Yeah, yeah. Successor true is in fact a normal form. Yeah. So yeah, this is what we're trying to say. We're just trying to say that we're trying to demonstrate that if you've got a well-typed term, it can't possibly get stuck. It must be capable of evaluation. You know, whether it's what you wanted to calculate, that's an entirely different conversation. But we can ensure that the internal logic is consistent. So, preservation. Proof will proceed by induction on typing derivations. We will assume that the above holds for all sub-derivations. Then we will proceed by case analysis of the final typing derivation. So, we will be checking the following. T true, T false, T zero, T if, T suck, T pred, T is zero. So, let's start with these three guys. Consider T true. We may immediately state that T is equal to true, and that the type is equal to Boolean. In this case, T does not evaluate to T prime. The left-hand side of our implication is false, so the theorem is vacuously true. So this is kind of an interesting one, right? It's like, we're trying to prove that these two guys imply this guy. If the premises are false, then we can conclude anything we want, really, which includes true, right? That's, actually, I should have used the, there was a comic, I should have used it up here. If you assume contradictory axioms, you can derive anything. It's called the principle of explosion. And then it's like a stupid thing. But yeah, so because the left-hand side here will end up being false, you can't say that the implication, like, it doesn't, anyway. Hopefully that makes sense. The theorem is vacuously true because the premises are contradictory. We immediately see that the exact same argument is applicable to T false and T zero, because these are typing rules specifically for values. So, consider T if. We may immediately state that the form of the term T is an if then else. T1 is a bool, T2 is of type T, and so is T3. Since we are trying to conclude that T prime has type T from T evaluates to T prime, as well as the type of T, we can also perform case analysis over the evaluation rules of the if expression. So this is like a nested case analysis, right? We're performing a case analysis over the term, or over the typing rules, and now we're going to perform a case analysis over the evaluation rules that are relevant to the term that we derived from our typing rule, right? So there are three evaluation rules which are applicable to if statements, or if expressions. We've got E if true, E if false, and E if. So, for E if true, we know that T1 will be true and that T prime is equal to T2, right? Because that's the evaluation rule. If true, then you take T2. We know that T1 is true, and we know that the evaluated term is T2 according to the evaluation rule. Since we have T2 is typed as T above here, we may therefore conclude that in this case T prime does have type T. We can perform basically the exact same analysis with respect to E if false, right? It's exactly the same, you're just taking T3. The fact that T2 and T3 are required to have the same type by the typing rule comes in pretty handy when you're trying to prove the type safety of the system, huh? So yeah, so now the only one that we have to deal with is the congruence rule. for E-if, we know that T1 evaluates to some T1 prime. And we know that if T1, then T2, else T3 evaluates to if T1 prime, else T2, else then T2, else T3. In this case, our induction hypothesis states that if we have T1 having some type, and T1 evaluates to T1 prime, then T1 prime evaluates to that same type. So, we know that T1 is a Boolean via our typing relation case analysis. We know that T1 evaluates to T1 prime via the evaluation relation case analysis. So we've got this one. We know the type of T1. We know that it evaluates. We assume that whatever it evaluates to is of the same type. So we can conclude T1 prime is of type bool. Since we have T1 prime is of type bool, T2 is T, and T3 is also type T, we conclude via our typing relation inference rule that if T1 prime, then we conclude via the typing inference rule that the whole if statement using T1 prime as the guard must have type T as a result, which is the same one. In all cases, therefore, we conclude that T1 or T prime has type T. What happens to this proof if we don't have T2? Yeah. Okay, so that's a fair question. So what happens to this proof if T3 and T2 don't have the same type, right? Well, it kind of depends, right? First of all, we would have like a T1, like T2 would lead to type T2, and T3 would lead to type T3, right? So you would not be able to say that these guys are the same, right? I don't think that it would necessarily break the congruence rule, because if the inference rule was set up in that manner, then when we used the inference rule here, there would be no requirement. There would be no requirement for T2 and T3 to have the same type, right? Because that would be the way in which we had constructed the inference rule. So I think the congruence one would just work. That would be fine. There would be no problem. The problem would be with E if true and E if false. So I'm gonna sneeze. So maybe I'm not. If T2 and T3 had a different type, like the thing that's not being said here is that this statement has type T as well, right? The if expression also has type T. So if T3, like what would the type here be if T2 and T3 were different, you know? You would have to come up with some way of determining that. Like, let's say, just for the sake of argument, that the inference rule stated that the type of the if expression is always the type of T2, regardless as to what T3 was, right? If that were the case, then if false, you wouldn't be able to hold it, right? Because what we're trying to prove is that when you evaluate this if statement, it will have the same type that it had before. But if if T3 has a different type than this whole term is typed as, and you perform the evaluation and you get T3 that has a different type, then preservation no longer holds. So if T2 and T3 had different types, our entire type system would be broken. We would not be able to guarantee that there are terms that can't get stuck. Right? We would not be able to guarantee that well-typed terms can't get stuck. Now, it would just be like one hole, right? We would just have the one case where this wasn't the case. So it's like, mostly it would be fine. But the exceptions matter, right? It's it's really important that you have, like, total compliance, because sooner or later someone's going to hit that exception and file a bug report. Yeah, and kind of the whole point of this class is learning how to design the mathematics so that you can minimize the number of bugs. But yeah, so that's our proof for T-if, which is the most complicated of them. Let's do T-successor. So from T-successor, we can immediately conclude that the term is successor T1, that the type of this term is natural, and that the type of T1 is natural, because of course we're assuming well-typedness. In this case, there is only one rule, E successor, which can be used for T evaluates to T prime, right? Successor only has one evaluation rule. From this, we know that T1 you must be able to evaluate T1 to T1 prime, right? Because it's a congruence rule. We're assuming the applicability of a congruence rule. Since we have this fact, with the fact that T1 is of type natural, we can conclude that T1 prime is of type natural by using the induction hypothesis, right? By using the induction hypothesis. Since we know that T prime is equal to successor of T1 prime, and T1 prime is of type natural, we can use our typing relation rule to conclude that T prime is of type natural. We have satisfied all of the conditions to reintroduce the typing rule. There you go. We can check the successor off of our list. Predecessor is the proof of predecessor proceeds along similar lines, but we've got 3 different evaluation rules to worry about with it. So, with predecessor, of course, the type of the term is natural, and the type of the subterm is also natural. Our evaluation rules are the congruence rule E-pred 0, and E-pred successor. The proof of the congruence rule E-pred is the same as the proof of E-successor, so we won't repeat it. Basically, it's exactly the same. The congruence rule proves out in exactly the same manner, so I'm not going to repeat myself. Consider E-pred 0. We can immediately state that both T prime and T1 are 0, right? Because otherwise, we get that from the fact that E-pred 0 was applied, right? Immediately, T prime is a natural number because of the typing rule of 0. Like, T0, the typing rule, gives us that T prime is a natural. So that's fine. That's fast and easy. Consider E-pred successor. We can immediately state that T1 is a successor and that T prime is equal to T2. To finish this case, we can use clause 5 of the inversion lemma, which states the successor of some term S1, if it's well-typed, if it has a type, that type is natural, and the subterm is also natural. If we set in the above, S1 should be S1 there. If we set this guy to T2, and then the successor of S as T1, then we know that T1 must be natural from our case analysis. We can therefore conclude that T2 must also be a natural from the inversion lemma. That is to say, T prime is equal to is a natural. So we know that this T1 is a successor, right? So we need to find out what the type of the thing inside the successor is. So we know that this guy must be well-typed because we've assumed that because of the induction hypothesis. So because of that, because it's well-typed, we know that the inner term must be of type natural. Since natural is the thing we're looking for, because that's the type of predecessor, we know that T prime is nat. Do I have enough time? No! Oh, Durant, I have run out of time to do the last 3 slides. So I guess we'll just have to do them next week. Alright, any questions? Any questions? Next week is going to be fun. We're going to get into gammas. We're going to have a new Greek letter on the slides next week. When we get into lambda calculus, you have to start worrying about what are called typing contexts, which is basically just a collection of typing rules which also inform further type calculations. So we're going to use the Greek letter capital gamma for that. All right. If nobody has any questions, then I'll log off here. Have a good weekend, as Aereo states. Yes. Have a good weekend, everybody. And, yeah, we'll see you next time. Same bat place, same bat channel, same bat time. All of that. I messed it up. So ashamed. Can't tell you what to do. All right. Have either a good or bad weekend. Ha! Perhaps we should perform case analysis on the different quality weekends that we can have. Something tells me that we would be here for a long time. I'll have a good weekend instead. Ha! Hoo-ha! I might, actually. We'll see. I don't know. Probably just going to be working on getting midterms ready for people. But not you guys, because I'm the best prof. That's why. Anyway. Remember me when you fill out your course evaluations. Take her easy, folks.